Looking at electric circuits. So here I have a simple circuit. I have one bulb connected and one resistor connected and three ammeters connected in different locations of the circuit. So we have a series circuit. um, so now what happens when we close the switch? So let's close the switch and see. So here I've closed the switch, and if you look at the value on the battery, so this battery supplies a magnitude of 34 volts. So that is my EMF. So this battery supplies a magnitude of 34 volts. That is my EMF. So that is the total uh, voltage supplied by the battery. But now let's look at how much of that 34 volts actually goes into the circuit. So I will take a voltmeter to measure the voltage around. If we look at that, you look at it's 32.64 volts. So that means only 32.64 volts actually goes into the circuit, which means the other 1.36 volts, that means it's lost. It's lost because of the internal resistance inside the battery. So 34, it's the EMF, so it's the total power supplied by the battery. But the voltage that goes into the circuit is 32.6 volts, because the other one, it's lost due to the internal resistance inside the battery. Now, if we look at our current, if we look at the three different ammeters located in three different places in the circuit, we can see that all three of them have the same current, which is exactly what we should know, that in a series circuit, our current stays the same. So in a series circuit, my current doesn't change. My current, the same current that enters a resistance and enters a bulb, is the same current that goes out of that bulb. So my current doesn't change. You can see even the ammeter, even though they're in three different locations, but in those three different locations, my current doesn't change. The only thing that will differ, so you must know, in a series circuit, current stays the same, and what happens is that your voltage is shared. So your current stays the same and your voltage is the one that gets shared. What do I mean by that? Let's measure the voltage across this resistance. So you see, if we measure the voltage across this resistance, we find that this resistance has a voltage of 19.04. Okay, what about let's measure the one here at the bulb. We find that the bulb has the voltage of 13.60. 13.60. So this bulb measures 13.60, and the voltage, as we said, measured 19.04. But look at this. So if I measure the voltage across both the battery and the bulb, it's that 32.64 which we saw across the battery. So that means that 32.04 that we found across the battery, it's shared between the resistance and the bulb. So it's shared between the resistance and the bulb. Yeah. So now, because what is it, current, the voltage is shared across the resistance and the bulb, that is the same, as you said, that is the same voltage that you find across this battery. But this is not the EMF, so this is the voltage. We'll call it the voltage external. It's the total voltage in the circuit, but it's not the EMF of the battery. The EMF of the battery will be this voltage plus the voltage lost due to the internal resistance. So now remember also one thing. So resistance resists current. So if you look at this, if I do this is my resistance, this is my battery, this is what you would have been more used to drawing. So change it back. So this is my resistance. So because resistance resists current, look at what happens when I increase resistance. So you see what happens when I increase resistance. Look at what happens to my current. See that? So my current keeps on decreasing. So when resistance increases, my current decreases. So which is the relationship between resistance and current? If resistance increases, current decreases. When resistance decreases, current increases. So it's a inversely proportional relationship. So current and resistance are inversely, we say they are inversely proportional. Why? Because when one of them increases, the other one decreases. Because you see, if I decrease resistance, look at what starts happening to my current. My current starts increasing. Even my bulb starts shining even more brighter because now there's more current. But once I increase the resistance, the bulb starts becoming even a bit dimmer. Because why? Because resistance is now resisting more current. Okay, so now look at what happens when I now change. So this is what happens in a series circuit. Current is the same, but voltage is shared. So what happens when I insert another bulb? Let's look at that. Oh, so put another bulb. Oh, look at that. You can see that the bulb on top is shining more brighter than the bulb at the bottom. But why do you think that is the case? We just spoke about it. On the bottom section, we have a resistance, and you said resistance resists current, right? Resistance resists current. So which means the bottom section will have less current flowing through it because of the resistance. Because less current is flowing through it, then the bottom bulb won't shine as bright as the top bulb. So the top bulb shines as bright because there's less resistance in this wire. Remember, current will always choose the easiest path, so the path that has less resistance. So because this path has less resistance, more current will choose that path. So you can even look at this. Look at the current here. It's 0.63, but the total current is 3,67. So which means 3 comma something of the current that's still left is where it went across the 10 the 10 ohm bulb, the bottom bulb, I mean the top bulb. So let's see what happens once I start decreasing my current, my resistance. So you can see I've decreased my resistance to 9 ohms now. Look at what happens. The bottom bulb also starts being brighter, and you can see my current increased, and also even the current at the bottom part increased. So my bulb is a bit brighter, so which is the relationship we explain. But now, as you can see, the total current is 4,504, but if you look at the bottom part, the current is 1,55, which means where is the other current? The other current is in the top bulb, which is exactly what the relationship between in a parallel line, in a parallel circuit. You say in a parallel circuit, current is shared. So that's what happens. Current comes, as you can see them split in there at the intersection. So they split, and then it comes together again here at this section. So that is why 4,50, at the end, it's still the same. It's still the same current. The current is still the same, which is 4,50. But when it reaches that point, it splits. Then what is it? More goes into the top bulb and less goes into the bottom bulb because of the resistance in the bottom bulb. So we say current is shared in a in a parallel circuit. But now voltage, let's look at what happens to voltage. So my voltage now is 29,50. So this is the voltage across shared now, because it's now 29,50 because I've increased more resistance as well. So let's look at this. Look at the voltage across the 10 ohm. It's also 29,50. Now let's look at the voltage across this bottom bulb, 15,52. Let's look at the voltage across the resistance, 13,92. I mean 97. But let's look at the resistance now across this 29,50, which you see that. So this shows us that in a parallel circuit, voltage is the same. So in a parallel circuit, voltage is the same. Obviously, this one, the reason why this bulb and the resistance, if I just look at this bulb, which is 15,52, and the resistance, which has a voltage of 13,97, the reason they have different voltages because both of them are in series. So they are in series. So the resistance and the bulb are in series. So they will share voltage because they are in series. But if I take them as one thing, you can see that the resistance, because the resistance and the bulb are in series, if I take them together and then compare them with the bulb on top, because both of them are in parallel with the bulb on top, so that means the bulb on top has what? They have the same voltage. So let's say I've removed this one, combine that, see that. So the bulb on top has you can see 28,83, 28,83. So in a parallel circuit, the voltage is the same across, and in a series circuit, there the current is the same. So you can remember that by it's VPSI. So Vusi plays in school. You can even say that Vusi plays in school. So VP um, IS. So that means voltage parallel, which means voltage is the same in parallel, and then current I, which is current in series. Okay. So some might ask, but okay, what happens? What happens? So I know if I increase resistance, my current becomes less. But what can I do to get more power? So you can get more power also by increasing obviously the total uh power supplied by the battery. So if I increase the total power, you can see what's happening. So if I increase my total power, that means the total power supplied to the circuit increases, which means the lights become more bright as well. Okay, but look at what happens. What do you think will happen if I put a wire across here? So if I put just a wire across the circuit. Oh, look at that. Battery is on fire. You see? So this is called short circuiting. So if you put a wire which has no, because this is why we're taking them as they are not taking them as no resistance. So if I put a wire, what do I do to my circuit? That we call it short circuiting. I'm short circuiting this circuit. Because why? Remember what we said? We said current will always choose a path that has less resistance. So which means if I put a wire, that means current will come, and then when it reaches this point here, you'll be like, oh, if I go down, I'm gonna get resistance, because the two bulbs have resistance. But no, there's an easier path that does not have any resistance. So what will happen? It's gonna choose that path. It's gonna choose the path with less resistance. So that is why you see this is called short circuiting. So because current will choose the path with less resistance. So that is why even like when you had resistance and bulb, you saw the current going more through this bulb, because it chooses the path with less resistance.